Okay, I'm going to do here with this pinkish purplish pen 9, 3, 1 through 6. This is some modeling with differential equations. And the basic model that we are interested in here is the model where we have amount of stuff whatever that stuff is, grows, or the amount can also shrink. I guess if I could say grow, the opposite of that is shrink, right? It grows or shrinks. In other words, the rate is positive or negative. The amount of stuff grows or shrinks at a rate that is directly proportional to the amount of stuff. That's the model. And the model for that is if P is the amount of stuff. We use P sometimes for like population or principal if it's like a bank account with money in it. The amount of stuff there is, the rate that's changing at is equal to some constant. This is the constant of proportionality. You could use K, use whatever letter you want. So the derivative is directly proportional to the amount of stuff. That's the differential equation. And then we can do separation of variables, and you basically get that PERT formula that you probably saw in pre-calculus. All right, so that's the game here. Number 1, A. Suppose that a quantity y increases at a rate that is proportional to the square of the amount present. So that means it's increasing. So the rate is directly proportional. There's my constant of proportionality to the square of the amount of stuff. And suppose that at time 0, the amount present is y sub 0. So at time equals 0, y is equal to, they're just going to call that y sub 0. Find an initial value problem whose solution is y of t. Well, this is the initial value problem. So if that's a little bit confusing what that means, this is, an initial value problem is a differential equation with an initial value that you could solve, but this is the problem itself. So it's a statement of the differential equation and the initial value. So if that was a little confusing in that one, see if you can do part B. Pause now and see if you can do this one on your own. Suppose that a quantity decreases at a rate that is proportional to the square of the amount present, and that the time at time 0, so same initial condition, at time 0, y is equal to y sub 0. Now there's two ways you can go here. You can either say that you can just do ky squared and say that k is that k is going to be negative, or you can say, well, I'm going to make it negative ky squared, and then k would be some positive number. Here, of course, k is going to be positive because it's increasing. So either way, it doesn't make any difference to me. The k, this whole thing here has to be negative, whether the negative sign is part of the k or whether the negative sign is in front of some positive version of the constant. It's got to be negative. All right. Suppose that a quantity changes in such a way that dy dt is equal to k times the square root of y. I'm going to write that in a more calculus-friendly k to the 1/2, where k is greater than 0. Describe how y changes in words. So this is like saying, instead of having the words that they gave us in 1a and b, can we look at this and can we like say the words? Sure. So we can say that the quantity that y increases at a rate that is proportional trying to use exactly the same words that they used in 1A. Proportional to the square root here of the amount present. You could say of just y, or if we're trying to copy them, amount present. That's the words you need to say. And then they want us to do the same thing here in B. I'm not going to recopy their little differential equation. I'm just going to say the words. That y decreases at a rate that is proportional to the cube of the amount present. And I think that's all we need to say there. All right. Number 3. Suppose that a particle moves along an s-axis in such a way that its velocity is always half of its position. Okay, so the velocity the easiest way to translate words into math is to try to do it as literally as you can. So the velocity is half of the position. And what did they use for s for the position? So that's the equation. Can we write a differential equation? Well, we know from, let's see, I guess we looked at this for the first time in Chapter 5 when we were doing applications of derivatives, and then again in Chapter 6 we talked about motion and all that. So we should know that, and actually as early as Chapter 3, we know that velocity is the derivative of position. So velocity is the same as ds dt, right? Velocity is the derivative of position. So why do we need to make that change to like satisfy the what this question is asking for? Well, this is true, this equation right here, but it's not a differential equation, and we couldn't use it to solve for position. This is true, it's just a restatement of this, but replacing v with the derivative of position. But this could be solved. You can move the s over here and the dt over here, separate the variables, and do some differential equation solving. So this is a differential equation that we can solve. We can solve it because this derivative is the same as the variable that shows up here. As long as this is only s's and t's in here, then we're good, right? Of course, this is a v and an s, two different things. And there's no derivatives in that either. All right, suppose that an object moves along an s-axis in such a way that its acceleration is always twice the velocity. So acceleration is twice velocity. Write a differential equation whose solution is s of t. So let's see, a differential equation whose solution would be s. So I want everything to be derivatives of s. Now we don't have to solve it, right? What is acceleration? Acceleration is the second derivative of position, and velocity is the first derivative of position. So again, how is it that this satisfies what the problem is asking for? This is a differential equation, in other words, an equation with derivatives in it, and the thing that's in it, the variables, are s and t. So this, if we knew how to solve this, we could solve it for s in terms of t. And we're not being asked to solve it, so that's all we need to do there. Just kind of, these first 4 problems are about understanding the language that we're dealing with here and what everything means. So hopefully that's making a little bit of sense. Number 4, suppose that a body moves along an s-axis through a resistive medium in such a way that velocity decreases at a rate that is twice the square of the velocity. Find a differential equation whose solution is a velocity. So we need to write down what that says. The velocity decreases, so the rate of change of the velocity, this is like what we were doing here, the rate of change of velocity, it decreases, so I'm going to put that negative sign there, and then my constant of proportionality. Oh, I don't need the constant. I know that it's twice. Sorry. It decreases at a rate that is 2 times the velocity. Right? We good there? All right. Oh, it's twice the square. Hold on. Twice the square of the velocity. There we go. So I need that there. Okay, so that's all we have to do for A. Just translate that into math. And then for part B, they want a differential equation whose solution is the position, S. So we just need to get to the S thing. So what is V is, this is the same as acceleration, dv dt, right? So if we want to turn that into position, that's the second derivative of position. Is all we need to do there, is equal to -2, and then V is the same as the derivative of position. So what's that game? We just rewrote things in terms of position, right? Because we know this relationship between acceleration, velocity, and position, that they're all derivatives or antiderivatives of each other. Oh, there's a used piece of paper. All right, now 5 and 6, we're going to actually try to take this a little bit further and you do what we were doing in 1 through 4, but then actually apply it to a particular situation. So in 5, we've got an initial population of 10,000 bacteria. So I'm going to call that P sub 0. P for population, that's the letter name I'm going to choose. You could call it Y if you wanted to. And at time 0, there's 10,000 of them. And it grows exponentially at a rate of 2% per hour. And Y equals Y sub t is the number of bacteria present t hours later. Find an initial value problem whose solution is Y of t. Okay, so the R is equal to 0.02, 2%. So what does this mean? It means the rate that it's growing at is equal to, I could say K here, but I know what that rate is. This is the 0.02 times the amount of stuff. And if we want this to be an initial value problem, we should include this. And P sub 0 is equal to 10,000. All right. Find a formula for Y of t. That's the same as asking for, they called it Y, sorry, I called it P here. Well, can you handle it being a different letter? Oh, I'm sorry, I'll change them to Y's, so I'm consistent with what the book's doing. So that's to say dy dt, and then that would be just changing all the P's to Y's to conform to what the book's doing. Okay, so now if they want to know, find a formula for Y of t, that's the same as saying solve this differential equation. So to do that, I have to separate variables. The dy has to stay on this side, and the dt has to move over here. That is not negotiable. So when the y moves over here with the dy, it's going to be 1 over y. And then the 0.02, any constant over here, I'm always going to leave that on the dt side. Right? So I just did algebra to this to turn it into this. Why is this the form we need it in? Because the y's are with the y's, and if there were t's, I would leave them over here, but there aren't any, so just the constant is here with the t. And now we do calculus. What's the antiderivative of 1 over y? Natural log y. And what's the antiderivative of 0.02, the number? It's 0.02 t. And like we talked about in the notes, I'm going to put a plus c on this side. Really, there's a plus c on both sides, and I'm just like subtracting the c that was over here to this, and it's like some other constant. So I haven't solved for that yet, which is why I can do that. And then I'm going to do e to the this, because I'd like to solve for y, which means I have to do e to the this. So e to the natural log y is just y. That's how we get that down. And then e to the 0.02 t plus c. And because of the way exponent rules work, this is the same as e to the 0.02 t times e to the c, and that's just some other constant. So this constant, when we get that up there, can come down. I'm going to call it c1 because it's not the same number as this, but I haven't solved for it yet. So I can move that down, and you can see now this is like the PERT formula that you learned in pre-calculus. And if at time 0, when I plug 0 in here, the amount has to be 10,000. And when I plug that in, y is 10,000 when t is 0. Well, e to the 0.02 times 0, that's e to the 0, that's 1. So the c, the constant, has to be that starting number, which is why we like to move that down there. So y is equal to 10,000 times e to the 0.02 t. That is the population as a function of time. Now, if you know how this exponential growth thing works, then you could have just taken this information and gone straight to here, right? Because like, oh, that's the initial value in the PERT formula. This is the starting value, and then e to the, this is the rate, and that's time. So starting value, e to the RT. But that's how you actually, that's why the PERT formula exists. This you didn't see in pre-calculus because you didn't know how to do calculus yet. See, how long does it take for the initial population of bacteria to double? Well, for it to double, that would be getting to a y value of 20,000. So to get to 20,000, and then be equal to this, and then I would just have to solve for like what t makes it get to 20,000. So I'm just solving that equation now. Divide by 10,000, 2 is equal to e to the 0.02 t. How do I get that t down from being up here? Take the natural log of both sides, because the natural log of e to the something, the natural log and the e to the e cancel out. So that's just 0.02 t. So t would be equal to natural log 2 divided by 0.02, which is about 35. And what's our time unit here? Is it hours? All right. And part D. How long does it take the population to reach 45,000? So that's the same exact thing that I did there, except now I wanted to get to 45,000. So 4.5 is equal to e to the 0.02 t. Natural log 4.5 equals 0.02 t. So that gives me about 75 hours, rounded to the nearest hour. All right. I think I can fit the last problem over here, number 6. A cell of the bacterium E. coli divides into 2 cells every 20 minutes when placed in a nutrient culture. So let y be the number of cells that are present after t minutes. Assume that the growth of the bacteria is approximated by a continuous exponential growth model. So that just means we can do all the stuff that we know how to do. When in doubt, assume that all the words that you don't understand are just giving you permission to do the thing that you know how to do. Good advice for the AP test. So find an initial value problem whose solution is y of t. So I guess we're just starting with one cell. Yeah. So y sub 0 is equal to 1, and it divides into 2 cells every 20 minutes. So what we need to do is find what that rate is. So we know that it's going to be like this kind of it's going to be this kind of equation here. But I don't know what the rate is. I know that it's doubling every 20 minutes. Do we want to do our time in minutes or hours? Let's see. We'll do it in minutes. So that means I know that I have an exponential growth model, which means that I know that it's going to be this initial value is 1 times e to the rt. I'd like to find what that r is. Now I know that the cell, it divides or doubles every 20 minutes. So that's going to turn into 2 from 1 after 20 minutes. Now I need to solve for that r. So 2 equals e to the 20r. Natural log of 2 is equal to 20r. So r is equal to the natural log of 2 divided by 20, 0.035. All right. And so the initial value problem would be like they described in 5, initial population y sub 0 is 1, and that dy dt is equal to 0.035 times y. We just had to find the r. Part B, find a formula for y of t. We really have that already, so y as a function of time is equal to 1 times e to the, after we found the r, times t. So you can go through the process of separating the variables and everything, but I know that it's going to turn out to be that, right? And C, how many cells are present after 2 hours? You could use the equation, or you could just kind of like run through the calculation. If at time 0 it's 1, and then 20 minutes later it doubles, 20 minutes later, 20 minutes later, 20 minutes later, 20 minutes later, 20 minutes later. It just keeps doubling. I think that's 20, 40, 60, that's 1 hour, 20, 40, 60, that's another hour, so 64. You could also, it says what, 2 hours later? So 2 hours is 120 minutes. So we should be able to get the same answer by plugging 120 into our model, right? So let's see if that works. So 1 times e to the 0.035 times 120. Now it's not going to be exactly 64 because I rounded that, right? But it should be pretty dang close. Right? The difference there is because of the rounding. All right, so either one of those answers is okay as far as I'm concerned. And then part D, how long does it take for the number of cells to reach 1 million? All right, well, just plug in 1,000,000 here. 1,000,000 is 10 to the 6. That's equal to e to the 0.035 t, and we're trying to figure out what that time would be. So natural log 10 to the 6 is equal to 0.035 t. This is taking the natural log of both sides, so I can bring that down. And then t would be natural log of 10 to the 6th divided by 0.035. I'm getting about 395 minutes. All right. That is how you do some exponential growth modeling with differential equations.